Now let's try another free response question. The table shows the behavior of f, which is continuous for all real numbers and where f of 1 is equal to 3. And the limit of f of x as x approaches infinity is equal to 0. Let's answer these questions. For what values of x is f decreasing? Does f have a relative minimum at x equals 3? Explain. Name the x value of the point of inflection on the graph of f, if any, and justify your answer. And then does the mean value theorem apply over the interval from 2 to 4? And justify your answer. And finally, sketch a possible graph of our function f. Let's get started. We will begin by answering the first question. For what values of x is f decreasing? Well, f is decreasing when the first derivative is negative. So if we look at our first derivative, or f prime of x, we can see that it is negative when x is less than 3. So therefore, it's decreasing on the interval from negative infinity to 3, not including 3, because f prime is negative. Now let's answer the next question. Does f have a relative minimum at x equals 3? Explain. Well, we can see that at 3, we go from negative to positive. So therefore, we are going to have a relative minimum there because our derivative is changing from negative to positive. Now let's look at part C. Name the x value of the point of inflection on the graph of f, if any, and justify your answer. Well, points of inflection are found when the second derivative changes from positive to negative or negative to positive. So let's look at our second derivative, f double prime of x. We can see that it's positive or concave up, then it doesn't exist at x equals 3, and then it becomes negative or concave down when x is greater than 3. That means that x equals 3 will be a point of inflection because our second derivative sign changes. Now let's answer part D. Does the mean value theorem apply over the closed interval from 2 to 4? And justify your answer. Now the theorem states that if a function is continuous and differentiable on a given interval, then there exists a point in that interval where the instantaneous rate of change will be equal to the average rate of change. So we need to determine whether or not f of x is continuous and differentiable within this interval. And we can see at the table, since we have a does not exist at the derivative when x is equal to 3. So therefore, we cannot apply the mean value theorem because f of x is not differentiable on that interval, despite being continuous. Main reasoning is because f prime of 3 does not exist. Now let's sketch a possible graph of our function f with the information that we're provided. We first know that f of 1 is equal to 3, so let's plot that point 1, 3. Next, let's look at our first and second derivative for x values less than 3. F prime of x is negative, meaning that it is decreasing. And f double prime of x, or the second derivative, is positive, meaning that it is concave up. So from 3 and less, we are going to have a decreasing and concave up graph. We know that f prime and f double prime both do not exist at this minimum value because we go from negative decreasing to positive increasing. So we're going to have a minimum point here, but because we're going positive and we have a negative second derivative, we're going to end up having a concave down section here. So it's going to look something like this. We're increasing and we're concave down. And then the last piece of information provided in the instructions is the limit of f of x as x approaches infinity is equal to 0. So I'm not going to pass through the x-axis again. Instead, I'm going to get closer and closer and closer to that x-axis and never touch it. So our graph's going to look a little something like this. And it is important to note that graphs can vary. And let's actually see how close we are with how this was drawn. That was actually really close to what the actual graph is.